The basic problem that's already been outlined in Franz Pretorius's talk, it's, of course, the era of gravitational wave astronomy is here. And I can tell you when I became interested in this problem, it was soon after the discovery. I found out that the gravitational wave event was more powerful, for an instant at least, than the power of all the stars in the visible universe. And that was really remarkable, and something that powerful, it seemed like something good to work on. Now, I do particle physics. I'm a particle theorist, and this problem is very far removed from what I normally do. So the question is, okay, what can we do? How can we contribute? And the type of work we want to contribute to is not something speculative, but something that would actually feed into the LIGO analysis pipeline to really try to do some work along those lines. So the question is, what can we do in particle theory to help with gravitational waves? And at first, it seems that these problems are completely distinct. So this would be an image of a particle collision. Two protons come in, they smash together, and out come all sorts of particles, including, there's even a Higgs boson somewhere in that. And the types of theories we use to describe that, it's non-abelian gauge theory, quantum chromodynamics, or electroweak theory. We use quantum field theory. And also you can notice that these are unbounded trajectories. The particles come in and they go out, and they certainly don't orbit each other. The gravitational wave problem is different. First, it's general relativity, not these theories. And also it involves classical physics, not quantum physics. And then also bounded orbit. So they seem to be completely distinct. But there is a simple observation that tells us we're at least in the right ballpark. And that's the fact that the gravitational waves are very long wavelength. They're very long wavelength compared to the size of the black holes. So for practical purposes, we can think of these black holes as point particles. If they're point particles, then that's good for us, elementary particle physics, right? And this idea, it's been around for a while, this basic idea that there is a connection between particle physics and gravitational wave physics. There's a paper, Iwasaki, 1971, also earlier papers where he used Feynman diagrams, the particle physics tools, to look at problems in the bound state problem of gravitational waves. And then this was systematized. Goldberger and Rothstein did that, and many other papers followed. And in fact, this way of thinking about the problem, is actually very well suited for pushing state-of-the-art calculations in perturbative calculations. Unlike Franz, I'm talking about perturbation theory. How do we approach general relativity? And the answer is not like anybody else. So we do not start with the Einstein field equations. We don't start with geometry. We start someplace else. This was understood first by Richard Feynman. Gravitons are spin-two particles. And from that information alone, you can construct the theory of general relativity, at least order by order in perturbation theory. Now, this way of thinking about the problem, it's very good for calculations in perturbation theory, but it's not suited for all problems. So it's generally designed for problems where you have asymptotically flat space-times in the context of perturbation theory. And gravitational waves is exactly in that category. Okay. Now, there's a few points. So it turns out we're actually very good at perturbation theory and particle physics. There's many problems that we have with gauge theories, collider physics, and then also theoretical issues like supergravity theories we think a lot about. But if you want to apply that to gravitational waves, there's two obvious problems that you have to deal with. One is generally, this is quantum, not classical. And so you have to understand how to take the classical limit of the quantum theory. And the other is this bounded versus unbounded orbits. And that is not a small problem. That you have to attack that head on to deal with that. In this talk, I'm going to say a few things about the modern approach to perturbative gravity that we use. And also I'll explain how we deal with these basic problems in the setup, that it's not exactly aligned with the problem of gravitational radiation from, say, two inspiraling black holes. Okay, just to be clear, this is the problem we're interested in. I think Franz had a very similar slide. And so we can think of this problem of the merger of two inspiraling black holes in terms of three distinct phases. They're distinct to us humans who use different techniques in the different places, but obviously it's just one process of the black holes coming together. So the first part is the inspiral phase. So the inspiral phase, we can use perturbation theory, especially out here. And as you approach towards the merger, then you have to use an improved perturbation theory. There are such things. There's something called effective one-body, other types of modeling, where basically you do some kind of resummation of the perturbation theory so you can come up right against the merger. And that's quite effective. In the merger, you need numerical relativity. And then in the ring down, there's again a perturbation theory that you can use. The part that we're interested in is this part. This is where the techniques are applicable. And it's also here, there's important work to be done to get high precision templates. So maybe just one comment about why we can't use numerical relativity for everything is if you need to generate 250,000 templates, you cannot do it numerically. It's literally too expensive. So you use a technique that combines all the information. Okay. Now, how important is this? Well, I'm a physicist, so the answer whether something is important or unimportant is, can it be measured? And this plot here, it basically, the way you should read it, if you see a dot that's low down, it means it can be measured. If it's high up, like up here, it cannot be measured. So in this plot, what they're basically trying to show is that these post-Newtonian orders, so it's orders of perturbation theory, that they can be measured at LIGO. And if they can be measured, if LIGO is sensitive to them, then therefore it's important. It's as simple as that. And actually, maybe one little amusing thing is how much better LIGO is than Hulse-Taylor, the original discovery of the gravitational waves, the indirect discovery. Because, of course, you very directly measure the waveforms. You have the detailed information, not just the fact that you're losing energy in the binary. Okay, so it's important, and over the years, people have been working very hard to get higher and higher orders of perturbation theory. The reason they do it is because it's important. It's no one wants to do a fourth post-Newtonian calculation unless it actually means something, unless you can actually use it in data analysis. So this post-Newtonian approximation, the way it works is you expand in Newton's constant, you expand in velocity. And that's based on the virial theorem that says in this bound orbit, v squared goes like gm over r. They're the same order. So this double expansion would be a very natural thing to do. And that's what Einstein did. So anyway, here's the Hamiltonian. The first two terms there, that's Newton. Then this is Einstein, Infeld, and Hoffman. That's the next order. And then over the years, people have been merrily working down the orders of perturbation theory. And so 2017, the fourth post-Newtonian was done. Actually, I had an email yesterday about the fifth post-Newtonian being done, but that paper still has to come out. So This is the basic setup that people have been using. Expand in Newton's constant, expand in velocity. Now, when we started this game, we asked ourselves, what can we do? Because if we're going to actually do something, we should do something that's actually useful, right? If you're trying to follow, we enter a new field and you try to follow what other people have done, and it takes you 10 years to get to the place where you can compete with them, that's not very good. So there is a variety of possible problems that we were looking at with spin, finite size effects, high orders of perturbation theory, and the question was, which problem should we solve? It had to be extremely difficult by standard methods. If it wasn't extremely difficult by standard methods, what do they need us for? It needed to be direct interest to LIGO theorists, maybe not directly to LIGO, but at least to the theorists who are close to LIGO. And very important to us, it needed to be in a form that, at least in principle, it can enter the LIGO analysis pipeline. And the answer of what we decided to do, it's called two-body Hamiltonian at third and fourth post-Minkowskian order. And I'll explain what that is. So when we got interested in this, this was one of the conferences, Amplitudes 2018, we had Alessandra Bunano come and explain the situation just so we could understand what the important problems were. And this is from her slide, which apparently is from someone else's slide. And what this shows are the terms that have been computed in post-Newtonian and what's also called post-Minkowski, which I'll explain in a second. So the post-Newtonian, you read down these columns, and those are orders in velocity and orders. It's 1 over r, but 1 over r actually means orders in g. So 0th post-Newtonian, that's Newton, and then Einstein, Infeld, Hoffman, and so on. If you read the rows across here, that's called post-Minkowskian. And we who do particle physics, we call that perturbation theory. It's just an expansion in Newton's constant and all orders in velocity. We like Lorentz invariance. So we want all orders in velocity, so it's Lorentz invariant. So this is the natural way that we would work in post-Minkowskian. And this post-Minkowskian approach, it's become much more popular in recent years, and that's independent of us. And Alessandra said, this is what needs to be done. Okay. So that was pretty simple. Here's when we, in 2017, a little bit before that workshop, there was this paper from Thibaut Damour, which is actually quite amusing in what he says, because I've never seen anything like this in all my years, where you get an invitation of what you need to do, right? We need some help. And there it is in the abstract. So this is quoted from the abstract. And we urge amplitude experts to use their novel techniques to compute two-loop scattering amplitudes of scalar masses from which one could deduce the third post-Minkowskian effective one-body Hamiltonian. I don't know about you, but I've never seen anyone say we need some help like that. But there it is. And it gets a prize for clarity. And so there you have it. It's difficult using standard methods. I mean, no one would ask for help unless it was difficult. It had to be of direct importance to LIGO Virgo theorists. Well, there's Thibaut, so it's important. And also, this doesn't state it here, but we understood that we needed to make it, whatever we do, it needs to be in a format that the output can go into the analysis pipeline. So how do we approach this problem? Well, let's go back to particle physics. We're talking about scattering amplitudes. For example, there's a graviton hits another graviton, and then it does something, and then 2 gravitons come out. So that's a scattering amplitude. And this you could think of in the context of quantum field theory. Okay, and there's a methodology which was developed for collider physics for a completely different problem for dealing with this. So that instead of gravitons, there would be quarks and gluons. And the basic idea is that in a gauge invariant way, and this is extremely important, the concept of gauge invariance, a formalism that's completely gauge invariant, that the way it works is it takes simpler gauge invariant scattering amplitudes, we call those the tree amplitudes, and it builds up the more complicated ones, higher orders of perturbation, which we call the loop amplitudes. I'll use that terminology directly. So you never pick a gauge. You always work with gauge invariant quantities. Okay? And there's a whole formalism for doing that, systematic formalism, where these particles are on shell. In the intermediate states, these are actually one particle states. So of course, we heard in Walt's talk infrared singularities, but never mind that. These are on shell in the sense that they're physical quantities, right? Physical in the sense of their gauge invariant, at least. Yeah. Okay, and later on in the talk, you're going to see these types of pictures, and they'll be in the context of the gravitational radiation problem. And so there's this methodology, which obviously I'm not going to explain here in any detail, for building scattering amplitudes using entirely gauge invariant methods. Okay, that's the key message. And it's a very efficient way of doing things. It led to something called the next to leading order revolution. That's next to leading order in perturbation theory in collider physics using quantum chromodynamics. Now, let's have a look at the difference between the perturbation theory of gauge particles, gluons. Let's say the 3 gluon vertex. You can open up a textbook in quantum field theory and you'll discover a Feynman rule. It looks like this. There's a matrix, it's called the color. There's a color matrix. It keeps track of the charges, the non-abelian charges. And this vertex describes the interaction of 3 gluons. This is the 3 graviton vertex in the Donder gauge. I mean, normally you pick a gauge. And if you compare these two, you see that the case of gravity is much, much more complicated. It's just a mess. Okay, if you look, this would be the standard way of doing perturbation theory using textbook methods. But this is not the way we're going to do it, because you already see the problem on line 1. Gravity is a mess. Okay? In fact, the way we should be thinking about it is gauge invariant. If we want it to be gauge invariant, we have to go on shell. We make these on shell particles. So this would be a gluon. This would be a graviton, a physical graviton, at least physical in the context of perturbation theory. And we impose the on-shell condition. That's Einstein's relation between energy and momentum. So it's physical, the transversality conditions, everything is physical. And then you discover something really remarkable, that in fact, the 3 graviton vertex, if these are placed on shell, in fact, it's 2 copies, the square, we like to call a double copy of the gauge theory one. You see, it's the same thing, except 2 copies of it. Gravitons are like 2 gluons. That'll be one of the key messages from this talk. We like to say that gravity is like gauge theory square. That's what you see here. Now, you'll say, okay, I'm not impressed because this is only the lowest order perturbation theory. It's only the vertex. I mean, you have to build up an entire formalism for computing all scattering amplitudes. In fact, that exists. And some of this was known a long time ago. There's Kawhi-Llewellyn tie relations. That comes from string theory. And what that does is it takes a 4 graviton interaction. So this is 2 gravitons come in, 2 out, and it relates it to 2 gluons coming in, 2 gluons going out, in a very simple formula. So these 2 theories are simply related. It's a double copy again. There's 2 copies. And in fact, this generalized is very general of what's called tree level. Okay, and then for loop level, we have what's called that unitarity method I showed you for building up the loops from the trees. So in this way, we can do gravity not by starting with the Einstein-Hilbert-Lagrangian. Forget that. We start with gauge theory. And using gauge theory, we then construct all information that we need for the gravitational wave problem. Okay? And by the way, just a little comment. So if this seems a little mysterious, it still is. If you look at the Einstein-Hilbert Lagrangian, and you look at the Yang-Mills Lagrangian, you can stare at this for a very long time, and you will not know why this is true. Nevertheless, it's true. One can convince oneself the hard way by just cranking out orders of perturbation theory and verifying this, or one can prove it, for example, using string theory. Okay? And it's really a remarkable fact. The theory of gravity and the theory of gauge theory, the other forces, they are very closely linked, much closer than you would have thought. Right? Because you think normally that gravity is a completely different kind of beast. It involves geometry, right? But in fact, in perturbation theory, for these scattering amplitudes, we see that they are extremely closely linked through the double copy, that all information for gravity already exists in gauge theory. Now here's another way of thinking about the problem, which is also, I think, pretty remarkable. It turns out the secret of understanding the structure, it's not to be found in gravity, it's to be found in gauge theory. And that's what we call this duality between color and kinematics. So this is, again, the 3-gluon vertex. And the 3-gluon vertex, it has a color factor, it has a kinematic factor. The color factor, these matrices, they satisfy Jacobi identity because it's based on a Lie algebra. The Lie algebra says that the color factors are related in a certain way. In fact, here it is, there's 3 types of diagrams. This fourth one can be absorbed in the other 2. And you get a relation between the color factors, and it's a homework exercise. I want to go home and verify that this is actually true, but you can verify that indeed these kinematic numerators, if you do the Feynman diagram algebra, these kinematic numerators, once you've organized things in terms of these 3 diagrams, that in fact these numerators satisfy the same Lie algebra, the same, I shouldn't say same Lie algebra, the same Jacobi identity. There's an underlying Lie algebra. And for those mathematicians who want to ask me, what's the Lie algebra? I don't know. But there clearly is a Lie algebra structure, a kinematic Lie algebra structure. There's a set of papers that describe that. I'm not actually going to say much more about that. But there's some interesting problem there. And in fact, this is very general. This thing holds at endpoints. There's basically, it says that the kinematic part of the gauge theory can be put into a form so that the kinematic part satisfies the same Jacobi identities that the color factors satisfy. And you say, okay, that's very nice. What are you going to do with it? And the answer is, what we're going to do with it, we're going to do gravity. If you want to do gravity, it's actually very cool. What you do is you take gauge theory, you arrange it so that this is manifestly true, that an amplitude can be written in terms of color factors, some kinematic numerator, and some Feynman propagators, and you arrange it so that all the numerators satisfy the same Jacobi identities. And you want gravity? Take the color factor, replace it with another numerator factor. This is quantum chromodynamics, that's Einstein gravity. So that's very cool. And that's the basis, you could say, of where we start from if we want to do gravity. And you're going to ask me, okay, what about outside of perturbation theory? And in fact, quite a bit is known about that. There's all sorts of examples. Schwarzschild black hole, Kira black hole. It's actually related to point charges in electromagnetism. The Schwarzschild one is directly a point charge through this double copy. And there's all sorts of other examples, solutions of cosmological constant, radiation from accelerating black holes, maximally symmetric spaces, so on and so forth. Unfortunately, there's no coherent story for this. It's just examples. A lot of this relies on special cases where you can use Kerr-Schild metric, and then you can figure out the mapping, this double copy mapping, how to relate the 2 theories. I think there's there's something maybe that can be done, maybe someone very clever, a mathematician, that looks at the data, there's all these examples, and then there's a coherent picture of what's going on, which is still lacking. Nevertheless, me being a physicist, I'm not having a coherent picture, that's okay, but can I calculate? Okay? And this question of scattering amplitudes, the field of scattering amplitudes, and gravitational radiation, there are actually quite a few people have looked at this, how to relate these problems, and various technical issues. But for us, the key question is, can we calculate something of direct interest to LIGO Virgo, to the theorists, decisively beyond the previous state of the art? Because if we don't do that, we're not doing anything too important, because you can keep on rewriting theories and showing relationships, but can you do something new is, of course, the key question. So that's what we set out to do. The way we approach this problem is what we're interested in is the two-body potential between two black holes. And we want it to high orders of perturbation theory. So the way we do it is we use all the technology and ideas, this double copy and unitarity and all the stuff that we know from particle physics for the gravitational scattering amplitude. And we combine it, from information from another subfield. It's called effective field theory. And this effective field theory is a way for us to use this information to extract the potential, to get the Hamiltonian. Right, so that's like the key thing you want, is you want the Hamiltonian of two black holes revolving around each other. Okay, and this basic idea, or this is the basic path that we take. And by the way, if you have a Hamiltonian, you've just solved that problem I was saying about unbound. We start with unbound, and we're interested in the bound orbit of two black holes revolving around each other. If you have a Hamiltonian, you can solve any problem you want, right? So that's why we want the Hamiltonian. Also, we want the Hamiltonian because what I said about the pipeline, we have to get, we want to be in a format so that it can enter the LIGO Virgo analysis pipeline. So you got to give them a Hamiltonian. Okay? How does this work? The effective field theory defines the Hamiltonian. We're interested in this potential. So this would be the generalization of Newton's potential. And we extract it by defining an effective field theory. The effective field theory, it's relativistic. There it is. It's a relativistic kinetic term. These fields A and B, they represent black holes. Remember, we can treat the black holes as point particles. So, through this effective field theory, we define an interaction, one black hole with another, through a potential. And this is done on ansatz, which you then are going to match to the full general relativity that we use all our technology for doing calculations of scattering. Okay? So the way it's done is two calculations in parallel, full general relativity, a scattering amplitude, and we take out all the heavy artillery. This is complicated, it's general relativity. You use amplitudes methods, double copy. You have to go to, h bar goes to 0, the classical limit. You have to do that quickly so you don't carry around extra junk. Use all the method, generalized unitarity. There's fancy loop integration techniques. There's a whole machinery that comes from particle physics on how to do that. You get an amplitude in general relativity. Then the simpler calculation that you do is an effective field theory. And there you build an ansatz, which gives you the potential. You just use some Feynman diagrams, nothing fancy. Then you integrate, and then you demand these two be equal. By demanding these two be equal, you determine the potential. You have the potential, you have the Hamiltonian. Our friends in LIGO are now happy because we would have a Hamiltonian for them. Okay, and just a little taste of how this, oh, that's funny. Huh. Some diagram disappeared there. There's supposed to be a diagram there. This might as well just point down here. There's a 3 vertex, like a 3-point amplitude. By Compton, it refers to like here, this would be a Compton, this would be a 4-point amplitude. And the basic idea is that you can glue together these bits and pieces, like these 3-point on-shell amplitudes, 4-point on-shell, 5-point on-shell, and you can use that to systematically build up high orders of perturbation theory. And one of the things that actually was very nice that we figured out pretty quickly is because we're interested in the black hole problem, 2 black holes, long-range interactions, that effectively means that there have to be these propagators here, and demanding that they're propagators there effectively means that it's on shell. So it just turned out that the problem we're interested in is very closely connected to the way we do things anyway, where you put a lot of lines on shell. And it also turns out that because you're interested in the classical limit, that there's other on-shell conditions on the matter, because it can't really be quantum. That means that these particles or these black holes, they always have to be on shell, like any physical particle or any physical particle. So the methodology is something that you could say is fit very well this problem that we're interested in of determining the 2-body Hamiltonian, fit very well with the techniques that we have. And just a little taste of how this is done. So this would be at what's called the second post-Minkowskian order. And so this would be a black hole comes in, another black hole comes in, and then there's order G square here. And the way you do that is these scattering amplitudes, these pieces, you just use these Kawhi-Llewellyn and tie relations to relate them to gauge theory. So we want gravity, but we immediately turn it into gauge theory. You multiply together these different tree amplitudes, and that's the object that you then have to integrate in order to get the more complicated scattering amplitude. And this would be an example of one of the amplitudes that feeds into this process. They're remarkably simple. Okay. This would be in gauge theory. They're remarkably compact. This is a spinor notation. It doesn't matter exactly what these are, but it's something that's determined in terms of the momenta of the particles. Okay. To make a long story short, there's all sorts of machinery that goes into this, like dealing with the integrals, for example. And there it is. This is order G cubed. That's what's called the 3rd post-Minkowskian order, the conservative terms, in the scattering amplitude. So this is a scattering amplitude taken to the classical limit, and it's in terms of some variables which are commonly used in the gravitational wave literature. It's just combinations of masses and momenta and things like that. Maybe one little comment is there's a little surprise here. This has a singularity in it. As m goes to 0, there's a singularity here. There's a log m. And that caused, shall we say, great confusion in the literature. Now, this object by itself, this is not for our LIGO friends, because this is a scattering amplitude. So this is not something they can use. You have to go through the effective field theory to then convert it into something that's completely usable. That's a Hamiltonian of the normal kind. Newton is somewhere in there, the very first term. This is relativistic, all orders in velocity. That's why you don't recognize it as Newton. But there's Newton. Einstein, Infeld, Hoffman is some pieces of this. And then there's a next order here. And the key is all orders in velocity. So we maintain Lorentz invariance. And by the way, that's something that's very important to us. We like to maintain structures. If there's some symmetry or some structures, we would definitely like maintaining that. Now, one thing that you're probably thinking about if you haven't seen this before is, how do you know this is right? You know, we come out of left field. We come from a different field completely, and then we attack the problem in this completely strange way that we start talking about double copy and color kinematics duality and all sorts of other stuff and unitarity, and you're wondering, okay, great, but did you get the right answer? So of course, the very first thing we did was try to compare the literature. So there's the post-Newtonian Hamiltonians. So that's in the literature, fourth post-Newtonian. So that had been done a few years back. And it's not completely trivial to compare because, as you know, a Hamiltonian is actually not gauge invariant. I could comment, it's a little ironic. I talk about working completely gauge invariant. And then when we hand the answer over, we go gauge non-invariant. But that's, of course, because that's what our friends in LIGO demand. They want a Hamiltonian. So then it's not gauge invariant. It depends on coordinates. So it takes some work to actually do the comparison. So the idea is we take our result, expand in velocity, and then try to match up to what they have after a canonical transformation. Now, after we did that, I say our friend Thibaut Damour, he seriously questioned the correctness of our result. In fact, he was explaining, and he wrote a paper where he explained all the things we'd done wrong and had some specific corrections. I took that as an opportunity to make a bet. I mean, what the heck? Get some nice French wine. So it took a while, maybe about a year or so. But in time, there are actually many calculations, high orders, new calculations in post-Newtonian, up to 6 post-Newtonian that overlap with us. And Damour is there. He did one of the calculations. And indeed, they verify our result. If you're curious what all this commotion was about, you can look at version 1 of his paper. And there are also other calculations that were done, but now it's accepted that we did it correctly. You know, I mean, it's just a scientific method. You know, you need some careful scrutiny, and we certainly got the careful scrutiny. Maybe here's just one little amusing thing, the comparison to the post-Newtonian Hamiltonian. So if you look at the post-Newtonian Hamiltonian, it looks quite complicated. There's 2 reasons for this. One is if you pick a gauge which is not so nice, then you make a mess of it, and that's part of the problem. And the other problem is that if you take something compact and you expand in velocity, like maybe that arc cinch, and there was a velocity and you expand it, then you just get some mess with some funny coefficients. But in any case, after the canonical transformation, we line up with this. There are some pieces, like the g to the 4th, g to the 5th. It's part of the post-Newtonian, but it's not part of the order post-Minkowskian. We work to order g cubed, all orders in velocity. Okay, I'll say more about the order g to the 4th in just a minute. Okay, so this works. Okay, the next question is, okay, it's a nice method. Can you go on? So indeed, we went on to the next order. So this is again, there's a scattering amplitude. It's at the next order of perturbation theory. This one looks a lot more complicated, but of course, that's life in perturbation theory. Each order gets a lot more complicated than the previous one. Just a couple comments about that. We encounter this polylogs and then elliptic functions. Luckily, these are very standard ones, so no problem there. There's other problems, the infrared singularity. So this is what's called potential modes. So no radiation was included in our calculation. And because of that separation, in fact, this answer is not complete. It's this 1 over epsilon, we use dimensional regularization. 1 over epsilon means it's infinite. So there's an infinity hiding in here, an infrared singularity. That singularity cancels once you put in the real radiation, the radiation pieces. We know that for a fact since we've actually done that. There's also some other pieces that are iteration. This is lower order stuff. We don't actually calculate it, we just identify it. some iteration pieces. And actually, one thing that's amusing is in this calculation, we realized what the heck the amplitude is. It's the exponential of what's called the radial action. So it's the amplitude in the classical limit. So it's like a quantum object, but we go at h bar we take h bar goes to 0, and you ask, okay, what is that classically? We now know the answer. It's the radial action. And the radial action is the object, which if you differentiate with respect to the angular momentum, you get the scattering angle. Two particles come in, they go out at a scattering angle. Okay? So that's a nice classical quantity. So in fact, this object we have calculated from the quantum theory, we now know exactly what it is in the classical theory. It's this radial action, or the exponential of the radial action. Just a few comments. So the thing that's actually can get pretty hard is integration. So somewhere, if there's something that looks like a Feynman diagram, there's an integral to be done. Those integrals can be very hard to do. But we in particle physics, we have a lot of experience with this, because when you do collider physics, high orders of perturbation theory, you need some tools. And indeed, there are tools. There is something called method of regions, which is what we use to separate out potential and radiation modes. That's one idea. There's some non-relativistic integration that we used in an earlier paper. But the really heavy hitter for doing loop integrals, to do integrals, is to use integration by parts method and differential equations. If you want to do an integral, don't do the integral. Find the differential equation. Much better way of doing it. And there's a whole technology of doing this. You download from the web. You find a program that does it for you. We use something called Fire 6. There's many of these programs that do these integrals for you and then allow us to construct differential equations. And that's how we get to very high orders, at least on dealing with those integrals. Oh, yeah, here's the two-body Hamiltonian. I'm almost done, actually. So this is order g to the fourth two-body Hamiltonian. It looks a little bit complicated. Well, it's high orders of perturbation theory. It gets a little messy. This is not a gauge invariant quantity, so I guess some mess gets caught in there. And this object, unfortunately, is not yet physical, because someplace hiding in there is an infrared singularity, which there it is. There's an infrared singularity right there. So this is an incomplete. It's half the answer, if you wish. Okay, but nevertheless, it's progress. And this time around, we didn't have any complaints about some issue with this. Anyway, it's been verified to high orders of other people's calculations in the overlap regions. So we're quite confident it's right. Soon after our calculation, even though it was incomplete, our friends in the LIGO collaboration, so this is Alessandra Buonanno, a theorist in LIGO Virgo, and her group, and her group, they took our Hamiltonian, even though it's incomplete. They said, what do we do about the infrared singularity? Oh, just throw it away. Let's have a look what happens. And this is the binding energy. So the binding energy is one of the two quantities that you have to feed LIGO. It comes straight out of the Hamiltonian. And the question is, how good is it? And there's a way of telling how good it is. What you do is you compare it either to numerical relativity or the effective one-body approach. So this is the professional grade stuff. And it goes all the way down to looking 3 orbits before it merges. And the thing that's very encouraging is that, in fact, our result matches very closely the professional grade contributions. Now, it's still incomplete, so you shouldn't get too excited, but of course, we get excited because it tells us we need to go and finish our calculation and get the missing piece so that next time around, there's not this drop 1 over epsilon. Okay. By the way, the 1 over epsilon is not there in the physical result. It's not the 1 over epsilon that's important, because that cancels. It's any finite pieces that are underneath that singularity. And that's what's missing. Okay, the outlook. So these methods have a lot of promise. They've been demonstrated in a variety of problems. The one I was talking about is pushing state-of-the-art, higher orders in G. There's other papers, there's a whole group of people working on this. Radiation, finite size effects, spin. They're all very natural in this quantum field theory approach. All these effects are included by higher dimension operators. You include just higher dimension terms in like corrections to Einstein-Hilbert, which then accounts for these different phenomena like the spin or the finite size of tidal effects, the finite size effects. But in any case, the methods they work, and we know they work because there's many state-of-the-art calculations that have been done either with spin or also in the finite size effects. Okay, so the summary is the elementary particle physics. It provides a new useful way to think about problems of direct interest to the gravitational wave community. The scattering amplitudes, one of the key characteristics why we like it. It's independent of gauges, coordinates, field variables, and it makes it much simpler to identify useful structures. It leads to more compact results because they're gauge invariant. And one of the key examples, there are other examples, but I spoke about the double copy. That's this relationship between gauge theory and gravity, which is apparent if you're working in gauge invariant quantities. Once you introduce coordinate dependence or gauge dependence, then the relationship between the two theories is completely obscure. And these methods, they work for a variety of problems. I spoke about the high orders of perturbation theory in this post-Minkowskian approach. We've gone to order G to the fourth. Okay, it's still half the calculation. We're working on the other half. And I think the most exciting part is that the methods are not exhausted. You know, we can see, for example, these integration by parts methods, how far that can go, and we're sure that it's going to go further. So the final summary is in the coming years, we can expect new advances not only in gravitational wave physics, but also in understanding gravity and its relation to gauge theory. Okay, thank you.